For assignment 9 and also for the participation for Unit 9, we're going to look at particle filters in robotics. We're going to look at some of the examples that come from the unit this week that Sebastian went over on particle filters. I'm going to start with the code that you'll download here is a simple particle filter example. There are quite a few folders here in this example. Our source code is broke up into three kind of namespaces. Something for the robot. This is not that important. It just actually has been used to control a robot before and stuff. But here it's just used to simulate a robot, not to control an actual robot. The GUI stuff is just the frame and the panel that's displayed, including the map that's displayed here. Most of the important stuff is under the particle filter. And the particle filter.java is the main routine that implements this particle filter, and we'll go over that in just a sec. And then particle is this each particle, so we're maintaining lots of individual particles. Each particle is like a prediction of where the robot might be. So we keep track of its X and Y location and its orientation, which way it's facing. We also calculate some distance measurements. We calculate the fitness, how close this particle is to the actual measurements the robot has. So we look at what sensor readings the robot has and what sensor readings this simulated particle might have, and we calculate a fitness. From the fitness, we calculate probabilities, and for all our particles, the probabilities add up to 1. And so these are, if we have like 1,000 particles, the probabilities are of any one out there is generally pretty low. So like 0. Like 1/10% or so, or less. Because all the probabilities of all the particles, and we often have 1,000 particles, are going to sum to 1. Let's keep track of a measurement, and this is related to the sensor measurements we have. We can look at different ways. Right now, this is set up to look at 9 different directions. From the robot, we look around in 9 different directions and measure the distance to the nearest wall in 9 different areas and do that. And this matches what is done with Sebastian. Now, in reality, when we actually do this with a real robot, this number is actually quite a bit bigger because we have a spinning LiDAR that looks around and might have 100 measurements around it. But for our simulation here, we're using this measurement of 9 measurements, again, because it matches quite well with what Sebastian shows. So let's just run this. I'm going to change this. Right now it's set up to not run very well by default, and your job is to look at some fixes. So I'm going to go down here and change this. Let's just run this. This is one version of it. This is of the solution. And again, here's a map of Tower Hall where my office is. This is actually just outside my office where we often test out the robot. So the actual robot, again, it's a simulated robot in this case, but is this blue? This is where the robot actually is. And all the little red dots are the particles, and they are guesses. And so originally we just randomly scatter them around. The robot has a location, also has a direction. There's little lines showing which way it's pointing, kind of a little nose on the robot. And again, each of these particles has a little nose showing which way it's facing. The little yellow dot is a guess of, given all the particles, where we think the robot would be. This is the particle system's best guess. And in a perfect world, this will be right on top of the blue. Now, as we move, I'm going to step forward here. So if we step forward here, we will get rid of we resample the particles. So we look at all the particles, and the ones that fit the measurements of the robot best are selected. So you can kind of see for each one of these particles, I don't do it for all, but just for certain ones of them, I draw out. So like this particle's here, and so it sees these measurements in its sensors. Or if the robot was here, it would see those measurements. And the robot's actually here, and it sees different measurements. And so based on comparing the measurements of one of these particles to the actual measurements that from the robot sensor, we give every particle a probability. So like this one doesn't match this one very well, and so this would have a low priority, where some of these would match this quite well and would have a higher priority. And then we resample all these particles, and we tend to pick the ones with the higher probability more. And so every time we take a step or we move, we resample the particles. So now again, most of the particles are right here next to part of the robot. Now it sees walls on both sides, and distance behind it and distance ahead of it. Now there are other particles here that are similar. This one and these could match that, and so there are other ones that could possibly. So I can turn left or right or go forward, and eventually with the different algorithms, all of my particles will be around the robot, and I will have localized the robot. So I'm pretty sure the robot is right here in this algorithm. And as I move forward or do things, the particles should stay about where the robot is moving. So that's the system you want to run. Now initially, we're going to run this, we're going to look at how it picks particles. Let's jump and review some of the methods that the particle system uses. So in the Unit 11 videos, Sebastian talks about particles and particle filters, particularly in this video 26. He walks you through an algorithm for creating particle, or for doing the particle systems. He has something called importance weights. We call that in our code the probability. And so we don't use W, we use the probability stuff. And he talks about looping through all the particles and resampling them as we go, and then also normalizing them. So you might want to review that video. He also, in this more advanced, the Audacity 373 video course, he goes into more detail here. One of the problems though is he's using Python in here. So he talks about creating new particles and how that would be set up. And this is an interesting video. You have to kind of skip over the sections where he's talking about Python, because again, we're going to be doing it in Java. But like this video 34.
Now it turns out this is not an easy thing.
Is good, and that's, I don't think I had that on the list here, but I should have. So you might want to go back and look at this. This talks about resampling the particles.
To do. An obvious idea might be to compute all these normalized alphas, but you still have to be able to sample from those. So in the spectrum of all alphas, you might draw a random variable uniformly from the interval 0 and 1, and then find out the alpha so that all the alphas leading up to it in sum are smaller than beta.
So he's talking about, again, they've got their fitness functions, and then they've normalized it, divided by the max, so that all these values, he's calling alpha and we're calling probability in our code, all the probabilities add up to 1. And then we're trying to randomly pick particles in here, and he walks you through, particularly in this code, this 35, he talks about a method for resampling with a wheel solution. So let's look at that.
So here's an idea how to make this more efficient, and it turns out empirically it also gives better samples. Let's represent all our particles in importance weight in a big wheel. Each particle occupies a slice that corresponds to its importance weight.
And in ours,
Particles
this is the probabilities.
With a bigger weight, like W5, occupy more space, whereas particles with a smaller weight occupy less space. Very initially, let's guess a particle index uniformly from the set of all indices. I denote this as a uniform sampler U from the discrete set of choices of index 1 all the way to n. And there's a caveat in Python, of course, it goes from 0.
Okay, so Sebastian's going to walk you through this in this video. So one way of thinking of this is that all the probabilities of all of our particles add up to 1. So if we denote them by the width of a pie, all the sizes of the pie will add up to 1 whole pie. And then what we're going to do is pick a random number between 0 and 1, and then we're going to start going over until we get there. So maybe we'll pick 0.5, and so we keep going through the particles until we get to that location. It's just one method for how you pick random particles when you know their probabilities and you want to try to pick them based on the probability. Now we're going to look at a couple different solutions to that, and so let's jump to our code and look at the code a little bit more. So again, I'm going to be focused on, in the particle filter part of the project, this thing called part filter, and I'm just going to walk you through the basics of that real quick. So we have an array of particles, and there'll be 500 or 1,000 particles, and you'll run this with both options. We have constructors here for setting this up and using this. So there's a number of constructors depending on how we have the map set up. You don't have to worry about that. There's methods for printing and displaying this, for drawing the particles on the map in different ways. And then we have to also move the particles or rotate the particles. In the same way we're moving the robot or rotating the robot, the particles also have to be able to move and rotate. So we have that. We have to update the measurements. We're going to pretend the particles have sensors and are checking measurements, so we can update those measurements. We do add some random noise, or we can add some random noise into this. And finally, we calculate the fitness, and this looks at the distance of the robot that the actual robot is getting on all of its measurements compared to the distance this particular particle is getting on all of its measurements, and we'll then calculate some fitness value of how well the sensor measurements on the robot match the sensor measurements on this particle. Now here's a routine for resampling the particles, and this does much of what we want to do with this, and this matches the algorithm, the loop that Sebastian says. So when he goes over this loop, this for loop, that is basically this for loop right here. So we're going to go, we're going to resample our particles. We have so many particles we want to do, and we're going to resample them. So what we're going to do inside the loop is we're going to pick a new particle, and this should be picked on based on the probability of each particle. So the particles with higher probabilities should be picked more frequently than those with lower probabilities. So we should do some sort of pick there, and we'll look at that in just a second. This is the routine you'll be playing with through this assignment. Is this one routine here? We'll look at 3 different versions of this. Now once we pick a particle, we add it to a new, well, we have to get it, we make a copy of it, then we copy, and we create a new particle. So this copies that particle basically based on this index we choose, and then we add it to a new array, and then we're done where we replace the old array with the new array, because remember we start with an array list of all our particles. So each time through we create a new array list, add particles to it, and recreate it. So that's what this resampling does. But you're going to focus on how do we pick particles. So if we want to pick particles based on their probability. So we have 1,000 particles, let's say, or whatever number of particles. How do you randomly pick one? So, I mean, how do you pick one and pick the more probable particles first? And so Sebastian outlines one method, the spinning wheel method. But there are other ways of doing it that are maybe more or less efficient, mainly less efficient, well, depending on their performance. So you're going to look at that. So there are actually 3 different routines, or 4 different routines. Pick particle 0. I'm going to change this so we're using pick particle 0 here. And when pick particle 0 just randomly picks a random integer and says we're going to use that particle. So it randomly picks it, doesn't look at all at the probabilities. And this doesn't perform very well. So if I run this program, okay, the particles are randomly distributed at start, but now if I move around, they clump together, but they're all over the place. They don't all get by the robot. In fact, there are really no particles by the robot now. They're all over place because, again, we're just randomly picking it. So pick particle 0 here calls this pick particle, and again, all it does is pick a random number and return that. So that's the default version, and it doesn't work. Now you're going to look at pick particle 1, pick particle 2, and pick particle 3. And these will each perform differently and pick the particles in different ways. So your job is to run this. So let's say we want to run pick particle 3. We would change this so that in resample particles we're doing pick particle 3. And we'd run this. And then we'd see how well pick particle 3 performed. Now all the particles are randomly set up around the robot to start, but now as I move forward, it should pick the particles that are closer to the robot sensor reading. So as I go forward, and I can also turn and go another direction here, but it should be centralizing, localizing the robot and the particles by where the robot is. Okay, so let's go back to your assignment here. So the first thing you want to do is run the program with that pick particle 0 and see that it doesn't perform well. Second, you want to pick one of the other 3 alternatives and run it and see how well it localizes the robot. Now you want to post a description of what this code to the discussion topics, and you can look at the participation posting, which will be right here, for details on that. Okay, and then you see that because you also want to post a reply to other people. So you'll have a discussion about how each of these different particle systems, or pick particle routines work. Your final thing for the assignment is to run the program with all 3 versions of pick particle. You can ignore particle 0, but 1, 2, 3, run it with all 3, and run it both with 1,000 and 500 particles. So here, this is 1,000 particles, and all of them should perform pretty well with that. And if I switch line 23 here down to 500, this doesn't take as much computation, but is a little more challenging on the program to see if it can localize with only 500 particles. So run each of the 3, particle 1, 2, 3, and again, all you have to do to change them is go into this particle resample particles and change which one it's calling. Here it's calling particle 3. So run all 3. Figure out which of, from your point of view, which of the 3 routines performs the best. Describe that, and also then provide a final description of how that particle system or how that method works. You might want to look at the discussions and see what's posted to discussions. Make sure if you are quoting anything from discussions that's not your own work to just cite it. You can just say as suggested by so-and-so in the discussion posts or something like that. Doesn't have to be a formal citation, but I just want to know when you're using other people's words directly in your quotes. Okay, that's the assignment. Hopefully you can have fun exploring particle systems. Again, this is a common system that's used in robot navigation, and we're using that in our robot right now.